Imagine this, astronomers thought 3i Atlas would simply slip by, a quiet interstellar passerby on its way through the solar system. Instead, it shocked the scientific world by erupting with a glow far brighter than anyone expected, 6 times stronger than the best models predicted. In just 2 days, it unleashed a massive green cloud of energized gas, stretching nearly half the width of the sun. For a fleeting moment, Earth's telescopes caught this spectacle, but now the comet is racing toward Mars at a speed that's nearly impossible to comprehend, disappearing into the blinding glare of the sun. To put that speed into perspective, this visitor is flying at about 58 kilometers per second, faster than any planet in our solar system. Even Mercury, the speed champion of planets, moves at only 48 kilometers. At this pace, Atlas could cover the distance between Earth and the Moon in just over an hour. Remember, the Apollo astronauts took 3 days to make that trip. And as it approaches its closest point to the sun, that speed will climb even higher, pushing close to 70 kilometers. For comparison, the Parker Solar Probe, the fastest spacecraft humans have ever built, had to use years of gravity assists to achieve speeds like this. Atlas manages it naturally, just by falling along its hyperbolic path. But brightness is where things get even more dramatic. Astronomers measure brightness with a magnitude scale, where lower numbers mean brighter light. The faintest stars visible to our eyes are around magnitude 6. Atlas recently jumped from magnitude 16 to 12, which may sound small, but that's a leap of about 40 times in brightness. Even so, don't expect to see it without help. To the naked eye, it's still invisible. Amateur astronomers with mid-sized telescopes describe it as a faint smudge, barely distinguishable from background stars. What they're actually seeing is the comet's coma, the glowing shell of gas and dust around its hidden core. Here's where Atlas stands apart from most comets. Its coma has expanded to nearly half the diameter of the sun. That's not a trick of the eye. It's a physical structure made of vaporized ice and dust, hundreds of thousands of kilometers wide. And the nucleus at the heart of this giant cloud remains a mystery. Estimates suggest it could be as small as 300 meters or as large as 5.6 kilometers across. But it's still buried inside that glowing envelope. Trajectory models make it clear. Atlas is a true interstellar visitor. It's not bound to the sun, and it will never return. It will skim past Mars at a distance of about 30 million kilometers, close on cosmic scales, but far enough to avoid any risk to the red planet or its orbiters. For Earth, its closest pass already happened, never dipping closer than 1.8 astronomical units, safely out of range. That means no impact threat, but it does mean we only have this one chance to study it. Once it slips behind the sun, it's gone forever, vanishing back into the depths of interstellar space. Astronomers around the world are racing to capture every detail before it disappears. Within hours of its sudden outburst, reports poured into Comet databases. Observers in Australia were among the first to confirm the six-fold brightening, sparking urgent questions. Was this a true physical explosion on the comet's surface, or just a trick of scattered light? Whatever the cause, one thing is certain, 3i Atlas is rewriting the rulebook for interstellar visitors. Each number, each measurement, seems to defy what we thought we knew, leaving us with one burning question. What exactly is this object revealing as it tears through our solar system? Right now, the clock is ticking. 3i Atlas is racing closer to the sun, and with every passing day, our ability to watch it from Earth fades. Astronomers call this angle of separation from the sun solar elongation, and once it shrinks below 30 degrees, the comet's faint glow is swallowed by the evening sky. By late October, that window closes completely, just as Atlas reaches its fastest, most active stage. The cruel part? That's exactly when it will be closest to Mars and blazing at peak brightness, yet invisible from Earth. At the end of October, Atlas swings around the sun at nearly 68 kilometers per second, a velocity that makes planets look sluggish. But because of the blinding solar glare, no ground telescope will capture this moment. It's like watching a thrilling movie, only to have the screen go black during the climax. For astronomers, it's a frustrating reality. The most spectacular part of the show will unfold beyond human eyes. That's why all hope now shifts to space-based observatories and orbiters near Mars. From the moment Atlas flared beyond predictions, a global scramble began. Schedulers at major facilities tore up their plans, slipping the comet into already packed calendars. The Hubble Space Telescope broke into its oversubscribed queue to grab ultraviolet and optical images, racing to catch detail before the coma grew too bright to measure accurately. Meanwhile, the James Webb Space Telescope was cleared for rare, emergency time. On August 6th, Webb locked its NIR spec instrument onto Atlas and immediately spotted something odd, a carbon dioxide to water ratio nearly 8 times higher than what's normal for comets in our solar system. That single measurement sent shockwaves through the community, hinting that Atlas carries chemical fingerprints unlike anything we've seen before. Other telescopes quickly joined in. Gemini South in Chile pivoted to capture rapid sequences of optical and infrared shots, tracking shifts in the coma's structure and color from night to night. NASA's SPHEREX, designed for sweeping sky surveys, adjusted its cadence to slip in quick checks of the comet's spectrum. Each observatory brought a different piece of the puzzle, but none could work alone. It took constant coordination, Slack channels buzzing with arguments about filters, exposure times, and scheduling, while data pipelines churned through the night to process frames before the next round of observations began. The urgency wasn't about fear of collision, it was about racing against the blackout. By early October, ground-based telescopes would be blind, leaving the fate of this investigation in the hands of space telescopes and orbiters beyond Earth's sky. If we fail to collect the data now, the mysteries of 3I Atlas, its chemistry, its structure, and its origins will vanish with it, sealed away as it escapes forever into interstellar space. When Earth's telescopes finally lost sight of 3I Atlas in the glare of the sun, the mission to study this interstellar wanderer didn't end, it shifted to Mars. Suddenly, orbiters that were never designed for this job became the front line of discovery. Engineers and scientists rushed to reprogram instruments, fight for observation slots, and push hardware to its limits, all to catch a comet moving tens of kilometers per second across millions of kilometers of space. NASA's Mars Reconnaissance Orbiter, famous for spotting objects the size of a desk on the Martian surface, tried to aim its high-rise camera at Atlas. With its razor-sharp moves or I-meter per pixel resolution, it might just capture the comet's hidden nucleus if glare and timing didn't overwhelm the sensors. But imaging a streaking comet from millions of kilometers away isn't routine science. Teams had to run endless simulations, adjust exposure times on the fly, and guard against the risk of frying pixels if the sun slipped into view. ESA's Mars Express joined in with its high-resolution stereo camera, built for wide landscapes of Mars but now repurposed to track the sprawling coma of Atlas. Its color filters teased apart dust and gas, while stereo imaging gave a 3D sense of the comet's growing cloud. Every exposure had to be carefully coordinated with ground astronomers, syncing Mars's vantage point with the comet's closest approach. Meanwhile, the Trace Gas Orbiter offered something Earth couldn't, a laboratory for chemistry in space. With instruments like Nomad, designed to sniff out faint gases in Mars's thin atmosphere, it could aim at Atlas instead, searching for the elevated carbon dioxide levels that Webb had already detected, and maybe for exotic compounds never before seen in a comet. Its imager, Cassis, snapped rapid-fire color images, watching for changes in the comet's glow from one orbit to the next. NASA's Maven orbiter brought yet another dimension. Its ultraviolet spectrograph tuned into emissions from oxygen and carbon, while plasma sensors measured how the solar wind tangled with the comet's outflow. This data could finally explain Atlas's eerie green glow. Was it the signature of atomic oxygen, or something stranger lurking in its chemistry? All of this required near-military precision. Mission control centers on both sides of the Atlantic held emergency meetings. Engineers weighed the risks of diverting instruments from routine Mars science. Software patches were uploaded at the last minute to enable new tracking modes. Every detail mattered. Cameras had to avoid sunlight, spectrometers needed recalibration, and dust hazard models were checked twice over. No single orbiter could do it all, but together they formed a network, a synthetic observatory orbiting Mars. For the first time, spacecraft around another planet became humanity's only eyes on an interstellar object. Each instrument, each dataset, was a piece of a much larger puzzle, and the pressure was immense. Whatever Atlas was revealing, this was our only chance to catch it before it vanished forever into the dark. Then came the most stunning twist. In September, Atlas's coma shifted color. What had been a muted reddish haze transformed into a brilliant green, stretching across a space nearly half the width of the sun. That glow wasn't just for show. It was chemistry on display, a fingerprint of volatile ices boiling off the nucleus. But the intensity of that transformation left astronomers wondering what exactly was happening inside this interstellar traveler to spark such a dramatic change. By September, 3I Atlas had transformed into something almost unrecognizable. Its coma swelled to more than 600,000 kilometers across, glowing with a vivid green light that couldn't be dismissed as a camera trick. This glow was real, intense, and puzzling. Traditionally, green comets owe their color to diatomic carbon, CO₂, which shines in the so-called swan bands when sunlight excites it. But when astronomers scanned Atlas with some of the world's most powerful instruments, Gemini, the Very Large Telescope, and even the James Webb Space Telescope, they found nothing. No carbon bands, no trace of the expected signal. Instead, the data pointed to something entirely different. Webb's mid-infrared spectra revealed a CO₂-to-water ratio of 7.6, an astonishing number, far beyond what we see in most solar system comets where water usually dominates. That pushed researchers to focus on atomic oxygen, specifically the rare green line at 5057 angstroms. This emission appears when ultraviolet sunlight and energetic electrons rip apart CO2 and H2O molecules, leaving behind excited oxygen atoms that glow green as they settle down. In Atlas's CO₂-rich coma, this process was running wild, outshining everything else and painting the comet with its eerie emerald hue. The absence of carbon signatures wasn't a failure, it was a clue. Atlas wasn't playing by the rules of local comets, it was showing us chemistry shaped in another star system, forged in an alien nursery before it ever entered ours. Lena Sato of the JWST team described it as chasing a moving target with a shifting personality, because every spectrum told a new story, revealing a comet in flux. Some researchers even considered alternatives like exotic plasma effects or hidden carbon monoxide fluorescence, but nothing matched the evidence as cleanly as atomic oxygen. The timing sealed it. Just as CO2 outgassing spiked, the green glow ignited, and then came another shock. Atlas displayed an anti-tail. Instead of streaming away from the sun like every comet tail we expect, a streak of dust seemed to point directly toward it. At first, astronomers thought it was a simple projection effect, a trick of perspective when Earth crosses a comet's orbital plane. But the geometry didn't line up, and the feature persisted for weeks. That persistence hinted at something deeper. The answer lies in Atlas's unusual chemistry and its uneven outgassing. Unlike water-dominated comets, Atlas is driven by carbon dioxide, and sunlight strikes its nucleus at steep angles, blasting jets from the sunward side. These jets launch heavy dust grains far larger than the fine particles carried by normal comets. Because they're bigger and slower, they can resist the sun's radiation pressure, holding their ground and creating a genuine physical anti-tail. Models suggest these grains are at least 10 microns across, big enough to endure the sun's heat and solar wind for thousands of kilometers before they finally break apart. That means Atlas isn't just glowing in alien colors, it's reshaping our understanding of comet tails themselves. The anti-tail is more than a curiosity, it's evidence of powerful jets, exotic dust, and a chemistry we've never seen up close before. Each observation makes Atlas less like a familiar comet, and more like a messenger, carrying a record of interstellar conditions we can barely begin to decode. When astronomers tracked the strange anti-tail of 3I Atlas, they weren't just looking at a pretty streak across the sky, they were watching nature bend the rules in real time. The anti-tail's light didn't scatter randomly like dust in a spotlight. Instead, its brightness fell off exactly as you'd expect, if solid grains were slowly burning away under the sun's relentless heat. These grains weren't ordinary flecks of ice either. Models showed they were huge by comet standards, at least 10 microns across, sturdy enough to resist the push of the solar wind, and survive far longer than typical comet dust. That survival gave rise to a true sunward arc, a feature that stayed visible for weeks when, by all normal logic, it should have faded. Plasma interactions added more drama. Charged dust grains twisted into thin streams and spikes, sculpted by the solar wind like brushstrokes on a cosmic canvas. But despite the eerie beauty, scientists kept finding the same answer. The physics was natural, just amplified to extremes. The anti-tail wasn't an alien artifact or interstellar tech. It was the raw mechanics of sunlight, gas and dust pushed to their breaking point. As one plasma physicist put it, before you claim the extraordinary, you have to rule out the ordinary.
And so far, the ordinary explains it all. But the real suspense is just beginning. 3I Atlas is racing toward perihelion, its closest approach to the sun, and no one can say for sure what happens next. Will the comet slowly fade, burning through its last reserves of volatile ice, until it becomes a dim ghost? Or will it suddenly flare, erupting as hidden pockets of gas burst free? Some scientists warn of a third, more dramatic outcome, complete disintegration. If the nucleus is as fragile and fractured as its wild behavior suggests, perihelion could shatter it into countless fragments, a final blaze before vanishing into darkness. Researchers are treating the weeks around perihelion like a cosmic stress test. Every scenario is mapped out with predictions. A smooth decline in brightness would mean steady outgassing, while sudden jumps or dips could reveal the nucleus breaking apart. If the comet's green glow lingers after perihelion, that might confirm deep stores of carbon dioxide ice. If the color shifts abruptly to red or blue, it could mean those reserves have been spent. The stakes here go far beyond one visitor from another star. 3I Atlas is a living probe from a distant nursery, carrying chemistry and structure shaped light years away. How it behaves tells us whether interstellar ices can survive eons of travel, how dust interacts with the solar wind, and whether our models of comet life cycles hold up when tested by the extreme. Every outcome, fade, flare, or fragment feeds new data into planetary defense strategies, sharpening our ability to predict the fates of cosmic wanderers that might one day pass too close to Earth. The next few weeks are marked with milestones. Mars orbiter data in early October, the all-important perihelion at the end of the month, and Earth-based observations resuming in November. Each will help confirm or shatter models in real time. This isn't just comet science, it's a live experiment unfolding at interstellar speed. And as history shows, even the best instruments can leave us with more questions than answers.